Now let us find the time complexity of the algorithm which finds the sum of n elements which are stored in an array using the recursive approach. So first let us write the recursive algorithm. Recursive sum A array comma n. What is A array? A is a one dimensional array which consists of n elements a1, a2, a3, etc. an, and n represents the input size, number of elements in the array. Checking if n is equal to 0. If n is equal to 0, then return 0, else return recursive sum of A array comma n minus 1 plus A of n. If else, end if, opening curly brace closes here. This is the end of recursive sum algorithm. As we obtained earlier, right, to evaluate S is equal to A1 plus A2 plus A3 plus etc. an using a recursive algorithm, that means a recursive sum of, let it be A array comma n. For the first n minus 1 entries, we can write as a recursive sum of A array comma n minus 1 and the nth entry is separated plus an. So a recursive sum of A array comma n is equal to recursive sum of A array comma n minus 1 plus A of n. That recursion is defined here. Recursive sum of A array comma n minus 1. This is added with the nth element in the array. A recursion termination condition is defined here. If n is equal to 0, then the value to be returned is 0. Let us introduce the count statements in this algorithm. Initialize, right, a count as a global variable and set its value to 0. Initial value of the global variable count is set to 0. Now writing count is equal to count plus 1 for the executable statements, that means for the proper program steps. If n is equal to 0, this is a conditional part. Condition may result in either true or a false. If n is equal to 0, then return 0. The condition may result in a true or false. So the condition is going to be tested. Checking if n is equal to 0 is taken as one step per execution to signify that before the if statement, let us write count is equal to count plus 1. This is corresponding to the if statement, conditional testing. If n is equal to 0, then return 0. Suppose n is 0, the value 0 is to be returned, right. So to signify that before this return 0, here introduce the count statement. Count is equal to count plus 1. This count is corresponding to the return statement. Else return, the expression is going to be evaluated and the value is returned to the calling place. Here return, right, some expression, but the expression involves the recursive statement. So assume, right, return some expression, value is there, the value is returned to the calling place. That stage, right, this return requires 1 increment, count is equal to count plus 1. But we need to analyze the algorithm. What will be the final value of count when n is equal to 0 and when n is greater than 0. So the proper count statements are introduced. Now assuming, right, count as a global variable which is initially set to 0, we need to find the final value of count. To find the final value of count, right, we need to check if when n is equal to 0, right, if n is equal to 0, here count is equal to count plus 1, right, one conditional test, return 0, right, count is incremented one time. So twice, right, count is incremented, twice, 2 times. Else return this expression, right, this is taken as one step per execution. So if we take t recursive sum of n, which defines the total number of executable steps in the algorithm recursive sum, we can have t recursive sum of n, this is equal to 2 if n is equal to 0. When n is equal to 0, the corresponding count increment is 2 times. So if n is equal to 0, t recursive sum of n is equal to 2. 2 plus, you have to find, right, the recursive sum for the n minus 1 array entries, right. For that we need to introduce the count, right, to 2 plus t recursive sum of n minus 1 if n is greater than 0. Because if n is greater than 0, what happens? We need to evaluate recursive sum of a array comma n minus 1. Then it calls recursive sum of a array comma n minus 2, n minus 3, n minus 4, right. Say if n is equal to 10, 9, 8, 7, right, etc. Finally, right, 3, 2, 1, then 0. So when n is greater than 0, the associated count is 2 plus recursive sum of n minus 1. How to write this 2 means, suppose n is greater than 0, initially you are checking if n is equal to 0, that count is taken as one time, but return 0 will not be executed. But when the control comes to else part, return count is equal to, before that, right, else count is equal to count plus 1, right. This includes the count for this return statement. So previously one time, 1 plus 1 2 times, that is the significance of this 2. 2 plus, yet to find the time needed to find right, find the sum of first n minus 1 elements in the array, that is recursive sum of a array comma n minus 1. If the time needed to find the sum of n elements in the array is t recursive sum of n, time needed to find the first n minus 1 elements in the array, right, to find the sum of first n minus 1 elements in the array is t recursive sum of n minus 1. So when clearly when n is equal to 0, this count is equal to count plus 1 and this return 0, right, count is equal to count plus 1, twice count is incremented when n is equal to 0. In case if n is greater than 0, if n is equal to 0, count is tested one time, return will not be executed, else count is equal to count plus 1 is executed twice, plus yet to find the time needed to find the sum of first n minus 1 elements using this recursive sum, right, call. So 2 plus find the time needed to find the recursion for the remaining n minus 1 elements. For n elements t recursive sum of n, for n minus 1 elements we can write T recursive sum of n minus 1. Understand? So the recurrence relation is this one, a T recursive sum of n is equal to 2 plus T recursive sum of n minus 1. This is true when n is greater than 0, and T recursive sum of n is equal to 2 when n is equal to 0. If we apply the substitution method to solve this recurrence relation, recursive sum of n minus 1, that is T of n minus 1, is obtained by putting n is equal to n minus 1 in the left hand side. So writing a 2 plus, putting n is equal to n minus 1, put n is equal to n minus 1 in, say, equation number 2. This is equation number 2, this is a termination condition, equation number 1. So in 2, right, putting n is equal to n minus 1, we have 2 plus T recursive sum of n minus 1 minus 1, that becomes n minus 2. So writing here, this is a 2 plus 2, or 2 into 2 plus T recursive sum of n minus 2. Extending the recursion one more stage, here put n is equal to n minus 2 in 1, T of n minus 2 is obtained. So 2 into 2 plus 2 plus T recursive sum of, putting n is equal to n minus 2, T of n minus 1 becomes T of n minus 2 minus 1, that is T of n minus 3. Simplifying this recursion, 2 into 3 plus a T recursive sum of n minus 3. Next stage, this becomes 2 into 4 plus T recursive sum of n minus 4. 3 means n minus 3, 2 means here n minus 2. This 2 is nothing but 2 into 1, that is n minus 1, etc. When a 2 into 3 becomes 2 into n, the required expression is a 2 into n plus T recursive sum of n minus n. N minus n means here n, 2 into n. 2 into n, right, we write a 2n plus T recursive sum of n minus n is 0. A T of 0, what is T of 0? T of 0 is a 2, using equation number 1. This is the termination condition. So putting the value 2 here, since from 1 T recursive sum of 0 is 2, so T recursive sum of n is equal to 2n plus 2 for all n greater than or equal to 0. This is a solution for the given recurrence relation. So it seems that the expression 2n plus 2, right, 2 is multiplied by n and added with 2, since the input size n is introduced in the right hand side 2n plus 2, 2n plus 2, right, this results in a linear computational complexity or big O of n computational complexity. So what is this 2n plus 2? 2n plus 2, which indicates that the total number of executable steps in the recursive sum of n elements algorithm, right. So the algorithm recursive sum, which takes a 2n plus 2 execution steps. T recursive sum of n is equal to a 2n plus 2 for all n greater than or equal to 0. This results in the linear computational complexity. We are discussing the step count method to find the total number of execution steps of the given algorithm. Now let us find the total number of execution steps for the matrix addition algorithm. Algorithm number 3, algorithm matrix addition, matrix add. Suppose A and B are two input matrices which are defined like this: A a two-dimensional array, B a two-dimensional array, and the resultant matrix is C. Assuming the dimension of the matrices A and B are m comma n. The parameter explanation: A is a two-dimensional array which consists of m rows and n columns. Likewise, B is a two-dimensional array which consists of m rows and n columns. These two are the input matrices. We need to find a matrix C which is obtained by adding the two matrices A and B. C is equal to A plus B. C is the resultant matrix which is obtained by adding the two matrices A and B. We need to write the algorithm using the for loop for I is equal to 1 to m do, then for j is equal to 1 to n do, then writing the assignment statement Cij is equal to Aij plus Bij. The corresponding entries in the matrices A and B are going to be added and stored into the corresponding entry in the resultant matrix C. For write inner for here, for example here n for, this is inner for, then outer for ends here, n for, opening curly brace, right, closing curly brace, this is the end of matrix add algorithm. Now we need to introduce the proper count statements. How to introduce the count statements? For I is equal to 1 to m do, in which the condition to be tested is I less than or equal to m. Checking the condition I less than or equal to m. This is the condition. To introduce the count for this conditional test, here right I am writing count is equal to count plus 1. Corresponding comment for this count is checking if I is less than or equal to m. Outer for, so when I is equal to 1, checking if 1 less than or equal to m, count is introduced. When I becomes 2, checking if 2 less than or equal to m, count is included here. When I becomes m, m less than or equal to m, a count is included in this count statement. When I becomes m plus 1, checking if m plus 1 less than or equal to m, we need to introduce the count. For that, right, this is the outer for ends here, right, outer for. After this outer for, we need to introduce the count statement. Count is equal to count plus 1. This is for the conditional test m plus 1 less than or equal to m, question mark. Understand? When I becomes m plus 1, the conditional test m plus 1 less than or equal to m is counted in this count statement, count is equal to count plus 1 after the outer for. Then for j is equal to 1 to n do, for each value of j, the condition to be tested is j is equal to 1, checking if j less than or equal to n. Then j is equal to 2, checking if j less than or equal to n. When j becomes n, checking if j less than or equal to n. J becomes n plus 1, checking if j less than or equal to n. So inner for loop, right, is also tested for here n plus 1 times, outer for loop is tested for m plus 1 times, right. In general, for I is equal to 1 to n, condition is tested for n plus 1 times, outer for loop m plus 1 times, inner for loop, right, n plus 1 times. So for each value of j, checking j less than or equal to n over the range of j is equal to 1 to n should be introduced here. Count is equal to count plus 1. This is checking if j is less than or equal to n over the range of j is equal to 1, 2, 3, etc. n. Because when j becomes n plus 1, checking if n plus 1 less than or equal to n, condition becomes false, control has to come out of the for, right, after the, right, inner for inner for ends here. After this n for, I am introducing the count. Count is equal to count plus 1. This count is to check if when j becomes n plus 1, checking if n plus 1 less than or equal to n, question mark. So inner for loop is executed for n plus 1 times. Associated count statement is returned here, this one and this one. Outer for loop count statements, this one and this one. Then the assignment statement Cij is equal to Aij plus Bij. Before this assignment or after this assignment, right, we can introduce the count. For example, here let us use count is equal to count plus 1. This count statement corresponds to Cij is equal to Aij plus Bij. So for all executable statements, the proper count statement is introduced here. Now we need to assume, right, if count is 0, count is 0, right, as a global variable, find the final value of count. To find the final value of count, right, here consider the for loop, outer for I is equal to 1 to m, count is equal to count plus 1. This count statement will get executed for m times. This is executed for m times, because I ranges from 1 to m. For each value of I, if I is less than or equal to m, then only control goes to execute, count is equal to count plus 1. So clearly count is equal to count plus 1, right. This statement is executed for m times. Then inner for loop, count is equal to count plus 1. Here count is equal to count plus 1. It seems that for each value of j, a count is incremented twice, right. For each value of j, a count is incremented twice. So to find out the total number of executable statements in this algorithm, right. So let us restructure this algorithm by minimizing count is equal to count plus 1 statements like this. For I is equal to 1 to m do after this outer for, we have the statement count is equal to count plus 1. Then consider the inner for j is equal to 1 to n do. So I write next for j is equal to 1 to n do. For each value of j, count is incremented twice. So writing this count is equal to count plus 1 and this count is equal to count plus 1, right, in a single statement. Here I am writing count is equal to count plus 2, twice the variable count is incremented. Then inner for, right, closes here n for. Now let us restructure this algorithm so that we can minimize the number of count statements. Consider the statement for I is equal to 1 to m do count is equal to count plus 1, that has been written as it is for I is equal to 1 to m count is equal to count plus 1. Then consider the inner for loop for j is equal to 1 to n do. For each value of j, count is incremented twice. So we can write the count statement in a single line. For j is equal to 1 to n do, count is equal to count plus 2. Then for, right, n for, after this inner for, count is incremented one time for the conditional test. J is equal to n plus 1, n plus 1 less than or equal to n plus 1 less than or equal to n. So after the inner for, count is incremented by 1. So here count is equal to count plus 1. Then for n for, outer n for, after this one time, right, m for m plus 1 less than or equal to m, a count is incremented by 1. So here count is equal to count plus 1. Now have a look into this inner for j is equal to 1 to n do count is equal to count plus 2 n for. Before the inner for, count is incremented by 1, after the inner for, count is incremented by 1. So these two count statements, right, can be written as count is equal to count plus 2. After n for, right, one time, right, count is incremented. Now count is equal to count plus 2, right. So simply write further write the simplification here. For I is equal to 1 to m do count is equal to count plus 2. For j is equal to 1 to n do count is equal to count plus 2. Then this n for count is equal to count plus 1. This is a simplified algorithm with the count statements. Now let us analyze the algorithm to find the final value of count, assuming initial value of count is 0. For each value of I, a count is incremented twice. So this statement count is equal to count plus 2 will have a significant of 2m times. I is equal to 1 to m, count is equal to count plus 2, right, will have a significant of 2m at times. For each value of j, here a count is incremented twice. Count is equal to count plus 2. For j is equal to 1 to n do count is equal to count plus 1 and Cij is equal to Aij plus Bij. We need to find, right, how many times the statement C is equal to C plus 2 will get executed. This for is controlled by the outer for. Outer for is executing for m times. This assignment statement is executing, right, twice. So 2n times, and 2n times, right, this is controlled by outer for loop m times. So this c is equal to c plus 2 is executed for 2mn times, 2n times, right, alone for this inner for loop, but this inner for is controlled for the outer for m times. So 2n into m or 2mn times the inner for loop is executed. Then c is equal to c plus 1, right, one time execution. So adding all these, right, we have t, the algorithm name is matrix add, t matrix add, parameters m comma n, problem instances, right, m and n, the dimensions of the matrices m by n. This is equal to 2mn plus 2mn is added, then 2m is added, 2mn plus 2m plus 1 is added. So this is the total number of executable steps in the matrix addition algorithm. T matrix add m comma n is equal to a 2mn a plus a 2m a plus 1. So the total number of executable steps are instructions in the matrix addition algorithm. This is in the order of the product of its dimensions. So this results in order of mn or a theta of mn, a computational complexity.